So today we're going to be talking about the spanning tree protocol, which is taming the switching loops. And we're talking about something that every network engineer fears, right? A broadcast storm. So I want you to imagine this scenario. It's a Monday morning. Let's say it's a Monday morning at Elpda Solutions Johannesburg head office. And then the staff, they arrive. They switch on their computers and nothing works. Just like when I got here this morning. So the switches are lit up like Christmas tree. They're like, every single LED is flashing at a maximum speed. The internet is down. The file server is unreachable. Every pings between PCs on the same VLANs are failing. So the entire network is completely paralyzed. So the help desk is flooded with calls, and the IT manager is getting messages from finance, from HR and from IT, and you, the network engineer, have to fix it. So what happened there? The answer is a switching loop. Someone, maybe a helpful but uninformed junior staff member, just plugged in a second cable between two switches just to make the network faster, or add a redundancy, and without spanning tree protocol active. So now that second cable created a loop, and that loop caused a broadcast storm that brought down the entire network in seconds. All right, now a broadcast storm on a flat 2-layer network can just saturate 1 gigabit of bandwidth in under 1 second. Just imagine that. So switch CPU will hit 100%. All user traffic stops. So in a real enterprise like maybe a bank or hospital, this is a critical severity 1 incident. Every minute of a downtime costs money, and in a hospital scenario, someone could die. It could cost lives. Now, why switching loops are catastrophic? Imagine switch 1. Let's say switch 1, the SW Johannesburg switch 1 is connected to switch 2 by 2 cables. All right, so a redundant link. Now a broadcast frame enters switch 1 on port, let's say on port 1, and then switch 1 does what all switches do. It broadcasts, so it floods the frame out every port except the one that it arrived on. So this includes both cables to switch 2, and then switch 2 receives the broadcast on 2 ports simultaneously. It also floods it, floods out every port, including the one that is going back to switch 1 and both cables. So switch 1 receives the broadcast again, and it floods it again and again and again. So the frame just multiply exponentially. So within milliseconds, the switches are spending 100% of their CPU processing those broadcast frames. So user traffic, your pings, your file transfers, your VoIP calls gets completely squeezed out, and then the switches just freezes. The network dies, right? So you can think about, let's take ESCOM, for example. They operate industrial control systems, right? ICS networks at power stations like Medupi and Kobeck, and that are converged with IT networks. So a broadcast storm on these networks could disrupt the SCADA monitoring system that control power generation. The Transnet Port Operations Network in Durban had a broadcast storm incident in 2019 that disrupted the container terminal operations for several hours. Now, STP is not optional in a critical infrastructure. It is a safety requirement. So redundant links are essential for enterprise resilience. So you absolutely need them for high availability, but without a mechanism to prevent loops. So those redundant links they kill the network. Now, spanning tree protocol is that mechanism. It lets you have redundant physical links without switching loops. So it gives you the best of worlds, rather, resilience and stability. Now, how does it work? How does STP work? So let's look at, for example, we've got switch 1 and 2. So we've got, let's say we've got switch 3 now that we're gonna put up. Now spanning tree protocol was invented by can't remember the name, but it was invented in 1985. Okay, you can look at the history, but anyway, we don't care about the history, right? So basically the goal was simple, was to allow redundant physical links in a switch network without creating a layer 2 loops. So the solution that was designed is elegant, so which is STP that identifies a redundant path and it blocks some ports just to break any potential loops. So if primary fails, then STP automatically unblocks the redundant path. So there's like an automatic failover, no loops, no storms. Okay, let's make an analogy so that you can really understand it. Let's look at so think of N1 highway between Johannesburg and Pretoria. So there is multiple routes. There's N1, there's N14, there's R101. The traffic authority, which let's call the traffic authority STP, identifies one primary route, which is N1, and keeps it active. So the alternative routes N14 and R101 are designated as a standby. So it's blocked to normal traffic. So if N1 is closed due to an accident, so let's say the accident maybe is a link failure, the traffic authority STP immediately opens N14. Traffic flows again, no chaos. So that is exactly what STP does for your switch network. Now STP operates in a 3-step every time it runs. Step 1, it elects a route bridge. Then step 2, it determines the best path to the route. Step 3, it blocks the redundant ports to eliminate the loops. So let me explain each step deeply. Step 1, it's a route bridge by election. So when STP starts, every switch thinks that it is a route. Every switch thinks that it is a route bridge. So they all send out the BPDU frames, which is a bridge protocol data frames units, announcing themselves. Now the bridge protocol data frame units contains the switch bridge ID, and then the bridge ID is an 8-byte value made out of 2 parts, a 2-byte bridge priority and a 6-byte MAC address. Now the switch with the lowest bridge ID wins the route bridge election, since all switches starts with the same default priority of 32768. So the tiebreaker is the MAC address. All right, the switch with the lowest MAC address becomes the route bridge. So in production network, we never leave the route bridge selection to to chance. So we always manually set the priority on the switch that we want to be a route bridge. Lower priority is more likely to be the route, and then the range is 0 to 61440 in increments of 4096. Now step 2, which is a port role assignment. Once the route bridge is elected, every switch determines the best path to reach it. So this determines each port's role. Rather, only one port on redundant link will be blocked, so the other ports remain forwarding, and the STP just finds the minimum number of ports to block to eliminate all the loops while keeping all device reachable. Rather, step 3 is port states. Now a port does not jump straight to forward when STP runs. It does through a series of states. So this is a 30-second delay that you sometimes see when you plug in a cable and a port light is orange before it turns green. So the worst case scenario, a port takes up to 50 seconds to go from blocked to forwarding. Now, or 20 seconds blocking plus 15 seconds listening plus 15 seconds learning. So this is why Cisco introduced port fast, which skips directly to forwarding for access port that are connected to the end devices like PCs, where the loop is impossible. Now, the BPDU, which is the language that the STP speaks. So remember, BPDU is a bridge protocol data unit. So it's a special layer 2 frame that switches use to exchange STP information. So it contains the root bridge ID, who the sender thinks is the root, and then the sender's bridge ID, who sent the BPDU, and then the root path cost, the total cost to reach the root, and the different timers. Now, BPDU are sent every 2 seconds, right? So it's like a hello timer by the root bridge on all its designated ports. Now the non-root switches relay the BPDU towards their designated ports. So if the switch stops receiving the BPDU for 20 seconds, which is a max age timer, it assumes that the root bridge is gone and starts a new election. On access ports data connected to the PCs, BPDU should never arrive. So a PC does not send it. So this is why the BPDU guard is so important. So if it arrives on access port, it means that someone has plugged in a rogue switch, and then the guard immediately shuts that port down. All right. Now that we covered some theory, we need to add a switch tree. So let's go ahead and add a switch. So I'm gonna add a 2960. Let's just put it somewhere here. So I'm gonna add the 2960. Let's go ahead and rename this switch here. So we're gonna rename it to SW JHB and then 03.1, and then we've got switch 2, and then all the 6 departments we added a third switch, which is switch Johannesburg 03, representing a new floor, maybe a new department area at the headquarters. And then we're going to connect both to switch 1 and switch 2, creating a triangle of redundant links. So we also need 2 PCs that we're going to connect. So let's add 2 computers there, or 2 PCs rather, that we will just connect. So let's name our PC. So this one will be let's name it management MT PC1, and let's somehow give it an IP as well. So I'm gonna give it an IP of 10.10.1.20. And then the gateway will be 10.1.1. All right, so let's do another one. So this one is going to be management PC2. So this one, let's make it 21. So it's going to be 10.10.1.21, and 255.255.255.0, and then 10.10.1.1, and then we're going to connect to port 1 and 2. Just All right, and then we're gonna connect switch 3 to switch 1 using a crossover cable. So we need to connect to okay, so let's see, I think we already connecting. Let's just remove this for now. The G, so it's G0. Let me just see. So that is G01. I need to connect it via G02. So I'm just looking for G02. Alright, so I'm gonna just delete this one. I'm gonna delete this one between between the second switch. Yes, because I need that G02. Remember, this one actually needs to go to the router. We're gonna put it back to the router. Alright, so we're gonna connect using crossover cable. So that is a G01 to G02. Alright, and then we need to connect G02 to Johannesburg G02, the crossover cable. So here we will just do G02 to switch 2, which is G02. All right, yeah, that makes much more sense. All right, I think so this creates some sort of a triangle. You see that it creates a triangle. On switch 3, we need to configure our VLANs again. All right, and set I think we use port 1 and port 2 as VLAN 10 access port, and then we set G01 and G02 as trunk ports, allowing VLAN 10, 20 and 30, and then the IP addresses for management PC1 we've already set that, which is a 10.10.1.20, and then the gateway is 10.10.1.1. So the same thing with management 2, which is 10.10.20.21, gateway is 10.10.1.1. So this continues from our 10.10.1.0/24, which is a finance or management VLAN scheme. All right, now let's go to our switch 3, which is this guy here, and then we will need to configure it. First enable and then configure terminal, and then a host name, which is SW JHP 3, and then we need to do VLAN 10. The name is finance, and then we need to do VLAN 20, and then name is HR, and then we need to do VLAN 30, and then name is IT. All right, so let's go ahead and do the access port interface, fast Ethernet 0/1, and so switch and and then let's do the same thing with the other port 02. All right, then let's do interface gigabit Ethernet 0/1, and then this one we make it a trunk, switch port mode trunk, and all right, so let's do the same thing with 2. All right, and then end. Now if you look there, you can see this forms some sort of a triangle. Now look at the topologies. The Johannesburg switch 1 and 2 and 3, they form a triangle. 3 switches, 3 inter switch links, a perfect loop waiting to happen. But before I show you the storm, let me show you that STP is already working silently to protect us. So let's click on Johannesburg switch 1, and then here we can just say show spanning tree, VLAN 10. Look at that. So look at this output carefully. I'm going to teach you to read it line by line, because this is the output that you will see in every CCNA exam question and a real world and every real world STP troubleshooting session. So the first section says root ID, right? I don't know if you can see that. Let me just highlight it. It says root ID. This tells you who's currently elected as the root bridge for VLAN 10. So you will see the priority is probably around 32778 or 768. This one is 778, and the MAC address of whichever switch won the default election. All right. We will also see the cause and the switch port on. So this switch faces the root. The second section says bridge ID. So this is this switch, which is the Johannesburg switch 1, its own priority and MAC address. And then the third section is the port table. At the bottom, look at the role column. Root port, designated port, and then the alternative or alternate, which means blocked. And then find the block port. So that is port STP has shut down to break the triangle loop. Let's do the broadcast storm demo. We're going to disable the STP. So this is demonstration only. Never disable STP on the production network. Okay, so this will cause a broadcast storm that will bring down the entire network. Now I'm going to show you what happens without STP. We're going to disable it all on 3 switches, and then switch to simulation mode so that we can watch the storm unfold frame by frame. So this is the most dramatic demonstration maybe in the entire lesson. I don't know. So I'm in switch 2. enable, make sure that the spelling is correct, and then configure no spanning tree VLAN 10, and then no spanning tree VLAN 20, and then no spanning tree VLAN 30, and then end. All right, now let's go to the other switch and then we'll do the same thing. Which one was I doing now? 2, ne? Let's do 3. So this one is already enabled, I think, so we can just say configure terminal, and then no spanning tree VLAN 10, no spanning tree VLAN 20, and then no spanning tree VLAN 30, and then end. All right, then let's go to switch 1. Okay, so at least now it will allow me to type. So say enable, and then configure a terminal, and then no spanning tree VLAN 10, do the same with 20, and then do the same with 30, and then end. All right, then let's switch to a simulation mode now. So we're gonna click on simulation, and then we wanna go and click on edit. I'm just gonna take this panel because I need to be able to see edit filters, and then just make sure ARP is ticked. ARP is ticked, and then ICMP is also ticked or checked. All right, so we're good with this one. And then let's go to finance PC1. From finance PC1, let's go and ping. We're gonna go desktop and then command prompt, and then let's ping 10.10.1. Sorry, it's 10. It's ping 10.10.1.235. And then now let's and then you can just press enter, and then let's look what's happening now on the canvas. Look at that, we cannot see finance 2. Did you say that? It couldn't ping finance 2. One broadcast frames enters switch 1. The switch floods it all. It actually floods all the port. So it hits switch 2 and then switch 3 simultaneously. And then both of them, they flood it back, and then switch one receives the frame broadcast again on multiple ports, and then it floods it again. So the frame is just multiplying every step forward. Is in the simulation adds more and more envelope icons on the canvas, right, until the screen is actually covered. So in real life, this will happen at a line speed, okay? Millions of frames per second, not slow motion like we see here in the simulation. All right, so within 1 second, the switches will be processing nothing but looping broadcast frames. So your ping from finance 1 to finance 2 to devices on the same VLAN will actually fail because the switch is 100% busy processing the storm. So this is what actually kills the network. All right, so now let's fix it by enabling the spinning protocol. So we can just go and fix it once more by Control C. Anyway, I press Control C there to stop. Control C, and then maybe we need this one, and then let's close reset simulation, and I'm just gonna close it, and let's go back to real time. All right, and then let's go and fix whatever that we did. So switch per switch. So I'm on switch 1 now, and then enable and then configure terminal. Configure terminal, and then spinning 3, and then VLAN 10, and then we do the same with 20, and then do the same with 30, and then end. So another thing is that okay, so let's go to the second switch. Another thing is that the port switch they had turned orange. You see that? So meaning they actually block. So now by enabling it, by enabling it again, they're gonna turn green. All right, so let's go to switch 2 and do the same thing. Actually, they turn green immediately after I've done switch 1. Let's do switch 2 and do the same thing. Enable configure so do spinning 3 VLAN 10, and then 20, and then 30. Alright, so let's do the same thing with switch 3. You'll see here, you must check, and then you'll see they will turn green now. You see they will turn green. Alright, so while we still wait, okay, there you go, you see they turn green. Alright, let's go to 3. So configure All right, you see also they turn green, and then these ones will also turn green. And just like that, STP is back. One port blocked, loop broken, and then network stable. So the storm is over.